The next component we're going to talk about is the inverter. This is the magic box that's turning that DC electricity from the module into AC that the utility grid can see. Inverters come in many different sizes and shapes and can be installed in many different locations on the building. The most important thing from a safety perspective to understand about inverters is that they need AC power from the grid to run. So if all you do is shut off their AC power source, the inverters will shut off. Now we'll focus more on this later, but for right now, just remember that to make the system safer, we do want to shut the inverters off. There are three main types of inverters: central, string, and microinverters. Central inverters are used on commercial and large-scale utility installations. String inverters are used on both residential and commercial installations. For both central and string inverters, the modules up on the roof are wired from one module to the next in series, and then finally down to the inverter. It's important to know that when the inverter is off, the strings up on the roof and the wires coming off may be at their maximum voltage when light's exposed. This is similar to closing the bail on a hose line. The pressure will go up a little bit, but there's no water or current, in our example, flowing. The pressure, or voltage again, is still there though. String inverters can be mounted up on the roof on commercial installations, pad mounted behind fencing, or more commonly in electrical rooms. This is one clue in identifying the presence of a PV system, by finding an inverter. Another very common inverter type is called a microinverter. These are installed under or directly attached to the modules, one microinverter for every module. In this type of system, because the microinverters also require AC power to run, when you shut off the main power to the building, the microinverter shuts down. The amount of energized conductors within the array is decreased. The only voltage still present is the wires from each individual module to that microinverter. Additionally, they are not wired in series. As an example, on a typical residential string installation, it could be operating at between 300 and 600 volts when the power is shut off to the building and the inverters are off. With a microinverter installation, there would be no more voltage than from a single module present when the power is shut off. However, in very cold conditions, the voltage can go up. So there would be a maximum of 80 volts present just for one module. Again, it's not in series, so it's not going to increase. So maximum of 80 volts. In a microinverter system, there is no string inverter on the wall. So one could say that the absence of an inverter on the wall could identify that microinverters are present up on the roof. The one problem with this is if you didn't find the inverter, it may only mean you just didn't find the inverter, not that the system has microinverters and therefore is a safer system. Nevertheless, it is always safer to reduce the voltage present in an emergency situation whenever possible. Another type of system that's becoming much more common from a safety perspective is called a DC optimizer. In these systems, there's a small box located behind every module and wired in series, then connected to a string inverter. What makes this type of system safe is that when the power is shut off to the inverter, each little box or optimizer under every module shuts down, similar to a microinverter, leaving only the voltage of a single module present within the array. Occasionally, the electronics are mounted directly inside the junction box in the back of the module. In response to fire service concerns for the inability to shut down an array in an emergency, installers are installing more and more of these types of systems, commonly called module-level power electronics. We'll discuss the codes more in another section.